So in this video, we are going to see the second method by which the processor and the input-output devices are going to communicate, that is interrupt. Okay, so in many situations, it is possible for a processor to perform other tasks while waiting for an input-output device to become ready. So in the previous case, that is in the programmed input-output, what we saw as a drawback is that you have to write enormous number of lines, and also each time the processor has to wait until that input or output device is ready. That is, the processor has to remain in that loop, keep on checking the status flag to see whether that device is ready or not. So that is actually a wastage of time. So to overcome that drawback, we are introducing interrupts. Here what it can do is, whenever the input output device is ready, it can raise a hardware signal which is called as an interrupt. So when this interrupt is being received by the processor can go and see what that particular device wants, whether it is a read operation or whether it is ready to display, whatever it is. Okay, so this is a hardware signal that has been generated, that is called as an interrupt, and one of the bus control line that is dedicated only for this is called as interrupt request line. Okay, so this is how transfer of control is being done using interrupt. Okay, this is an example where you have two programs. Here in this particular example, the first program is a compute routine and the second program performs a print. Okay, so compute is any kind of computation. So whenever the computation is being done, correspondingly that computed answer is given to the display device or that printing program. Okay, so that is what is the programs are doing. So in this example, as you can see from the diagram, when it reaches ith line, one computation might be finished and that computed result need to be displayed in the device. So whenever this particular instruction reaches, at this point an interrupt is being called, which will move the program counter to that particular program 2 where it gets displayed. Once that display operation is finished, then it will come back to the main program and it will continue execution from the i+1th line. This process will continue. Now this looks very familiar with how a subroutine is being called in a program, right? So the most common question that is asked from this part is, what is the comparison between an interrupt and a subroutine, or how are interrupts and subroutines related, or what is a disadvantage between a subroutine call and an interrupt call? So these are some of the questions which usually come from this part. So we'll see how it is being done. So the routine that is executed in response to an interrupt is called as an interrupt service routine. So this is similar to subroutine calls. So whenever the computation is over by the compute routine, a request is being given by the printer. That is, whenever the printer is ready for printing, it will interrupt the device. The first program execution gets interrupted and the processor now switches to give that display device the corresponding output that is given from this particular program. So this is similar to the subroutine call. So that is called as interrupt service routine. Okay, so that interrupt request is called as an interrupt service routine. Okay, now another thing that is similar between a subroutine and this interrupt service request is that whenever a program switches from the main program to the subroutine call, what it will do, the content of the program counter, the current pointing program counter is i+1. This i+1 will be saved into some stack or register, right? Similarly, in an interrupt service routine also, whenever the processor switches to that particular device for servicing that interrupt, this i+1 will get saved into the processor's stack. Okay, so this is the way how both of them are similar. The interrupt service routine and the subroutine call are similar. Now, where is the difference arises? Okay, the difference between an interrupt service routine and a subroutine is that you might have noticed that a subroutine is always called from a main program in order to perform some specific task related to that main program itself. That is, in a way, the main program and that subroutine program are related. Always they will be related. But in case of an interrupt service routine, both these programs will not have any relation. Okay, that is, sometimes the program that is getting executed might be of getting some inputs from the keyboard or something like that, but an interrupt that will be received to the processor will be from some output device or from some other input device. So in a way, these three things are not related at all, right? So in the first case, that in subroutine calls, the programs, the calling program and the called program, both of them will have some relation. But in case of an interrupt service routine, it is not necessary that there should be some relation between these. So in case if there is no relation, then what all are the things that need to be taken care of? Since there are no relation, there is a possibility that informations may get altered during the execution of a routine. So those information needs to be saved inside a stack or a register. So the current executing programs information need to be stored inside the processor's stack, because there is a possibility that it could get altered if you go back. If you go to that called program and if you come back, that registers might have get altered. So it is always necessary that you need to store these values somewhere. So that kind of information usually is condition code flags, content of the registers, etc. So these condition code flags and content of the registers, they need to be saved in that processor stack, and once the interrupted program's execution is completed, it will return back. Okay, and it will get the result back from the stack or the register. Now this process of saving, whenever an interrupt is arised, the process of saving the current execution details and going to servicing that request will take some delay. That delay is called as an interrupt latency. So what is interrupt latency? Saving the registers increases the delay between the time an interrupt request is received and the start of execution of an interrupt service. Okay, so immediately after the interrupt request is received, it cannot go back and service that request because it has to save the content of the registers. So that will create some kind of latency. Okay, so in some computers, they might opt for saving the content of all registers, and sometimes in certain computers they do not opt for saving the content in order to save this interrupt latency. Okay, delay that is caused due to interrupt latency. So there are two ways by which this interrupts can be generated in computers. Okay, so this same concept of interrupts can be used in operating systems and also in many applications. So hence it is referred to as real-time processing. Now next we are going to see the hardware component of an interrupt. So this is the hardware that is required, or the circuit that is required to generate an interrupt. So these are different input-output devices that are connected through a line to the processor. So INTR 1, 2, N it denotes the interrupts that are generated by devices 1, 2, 3, etc. Okay, so to request an interrupt, the device will close its associated switch. So all these switches are initially now grounded, and the voltage that is present inside this INTR line is VDD. Okay, so this is now high voltage, and all these devices are now in an open state. So when these switches are open, the voltage is high. Now if any of these device wants to raise an interrupt, what it does is it will close the switch. Once closing the switch, then it will give a value 0, or the voltage 0 is now present inside the line. Okay, so when no interrupts are there, all switches are open and the voltage will be VDD. When a device requests an interrupt, it will close the switch and the voltage will drop to 0. When the voltage drops to 0, since this is an inverter symbol here, this 0 will get inverted to 1, and then the processor will identify that if 1 is present in this line, it means that some of the device has, or any of the device has raised an interrupt. Now all these devices are connected in an OR arrangement, or a gate is a logical OR. So if multiple devices are raising an interrupt also, the line will have a 1 signal, or the voltage will drop to 0 and the inverter will give a 1 to the processor, indicating that multiple devices have raised an interrupt. And the gate that is used here in the INTR line is called as an open collector gate or an open drain gate. It is a special gate in which what it denotes is that it is equivalent to a switch to the ground, that is open when the gate's input is in 0 state and it is closed when it is in 1 state. That is, an open collector or an open drain gate is when it is 0 and when it is 1. That is being denoted here. Okay, so when it is when the switch is grounded, it is open when the gate's input is in 0 state, and the gate is closed when it is in 1 state. So whenever this particular gate is closed, that means that here a 1 is generated, the signal here is 0 and it is inverted, and a 1 is given to the processor. So whenever these gates are closed, there is a 1 that gets generated in the INTR. Okay. Now how you can enable and disable the interrupt. Okay, so there is a possibility that interrupts can arrive at any time and they may alter the sequence of events planned by the programmer. And also we have to make sure that an active request signal does not lead to successive interrupts. That is, once an interrupt is being generated by device 1, we should make sure that again device 1 should not generate an interrupt, right? So if it continuously goes on, then an infinite loop will be generated. That is, it will continuously go on servicing the interrupt of device 1 and the processor will not be free. So in order to prevent that, there are 3 possibilities to ensure that this infinite loop doesn't occur or successive interruptions do not occur. In the first method, the processor hardware will ignore the interrupt request line until the execution of the first instruction of the interrupt service routine. That is, only once the interrupt service routine execution starts, then only the processor will enable its interrupt request. Until then, it will not service any request. Okay, so once the first line of the interrupt service routine starts execution, then only the interrupt line signal will be enabled. That is, the first instruction in the interrupt service routine will be a disable interrupt. Once a device interrupt is received, then immediately it will give a disable interrupt in the signal so that it will not accept any more interrupts. And the last instruction in the interrupt service routine, once that interrupt service routine is serviced, then the last instruction will be an enable interrupt. In that enable interrupt, then it will start accepting the interrupts. In the second method, the processor will automatically disable the interrupts even before starting the execution of the interrupt service routine. That is, even before starting the request or even before starting servicing that particular request, it will disable any further interrupts. It will enable the interrupts only once that interrupt service routine is finished execution. And in the third method, the processor has a special IRQ line, that is that for which the interrupt handling circuit will respond only to the leading edge of the signal. That is called as an edge triggered. Okay, so the processor will receive only one request regardless of how long the line is activated. So in this third method, the processor will receive only one particular device because it will respond only when it is in an edge triggered format. So these are the sequence of events involved in handling an IRQ request, which we have already seen. First method is device raises an IRQ. Second, the processor will interrupt the program currently getting executed. The interrupt is disabled by changing the control bit in the processor stack, and then the device is informed that the request has been recognized by giving an acknowledgement. Then the action required requested by the interrupt is being performed and the interrupts are enabled and execution of the interrupted program is resumed. So these are the steps that are involved. So always remember that whenever a request is being received by the processor, before it starts servicing it, an acknowledgement is given to that device to denote that the processor has taken up that particular request.